stand up.
Oh, man. And do the professors get to yell
You
at
never
him?
want to be the professor who turns around and sees your entire class.
The stream is ready to go, Hannah, so whenever you're ready.
That was a dream of mine once to teach a 100 class at the Naval Academy. If somebody gave me some cheap excuse, I could just get right up to their face, you know, and yell at them about it.
Like starting to like work on code, it takes a while to get started.
You can see
By the time I just start reading stuff.
What? Yeah, I got it. Until.
How are you doing?
I got it now. It took me a second.
It was pretty bad.
It was very bad. All right, welcome to Colloquium, everyone. So a couple things before I introduce Anand. So remember that this is a collegial environment, and it is okay if you are still learning, and the questions you ask are maybe not the most intense things. That's not the goal of this. We're all here to kind of learn something new. So please keep that in mind as we kind of go through this talk. The other thing, of course, is that grad students are always encouraged to ask questions first, and then we open it up to the faculty and everyone else. So please do that. Otherwise, I will not keep it collegial, all right? No, I'm not that terrible. All right, so it's my great pleasure to introduce Anand Gnanadesikan. He is a professor in the Department of Earth and Planetary Sciences at Johns Hopkins University, where he's been since 2011. That's when I first knew Anand, so I guess it's been 11 years now. It's pretty wild. I don't like that I can mark things in my life in decades.
Did you actually take physical oceanography from me that fall?
No, you were gone. You left it, you started in January 2011, and I did not start until fall 2011. Yeah,
So I taught fall 2010.
it's okay. So prior to that, several years prior to that, he got his PhD in physical oceanography from the MIT Woods Hole Joint Program. And then he kind of worked at Princeton in the NOAA Geophysical Fluid Dynamics Laboratory for about 15 years before moving to Johns Hopkins. So that was, like I said, where I tried to overlap with him, but he wouldn't allow me to. And I like to tell people this every time I see him, every time. So for 11 years, he's been dealing with me bothering him.
Sounds like it'll be for 11 more.
Yes.
Hopefully more than
Keep it up, John.
Hopefully more.
Right. So his overarching theme for his research is really the interaction of living things with their physical environment, and specifically how the ocean circulates, and how that actually impacts marine life, climate, atmospheric chemistry, other things. Biology. We could describe him as a biological oceanographer now, I think. No. He's okay. I won't do that to you. And so today, Anand is going to be talking about ocean convection. So I think a lot of you like to think about convection in the atmosphere. We could also think about it in the ocean, yes. And so he'll be talking about where, when, and why we care about ocean convection. So go ahead and take it away.
Thank you, Hannah. And thank you for having me. It's a real pleasure to be here. A lot of friends and colleagues in this department that I've known and admired for years. So, as Hannah said, many of you think about convection in the atmosphere. I want to start off by convincing you that yes, convection really is a thing in the ocean. This is some recent measurements from the Gulf of Lyon, where the top plot here is looking at heat flux, and you see these times of negative heat flux, and temperatures, salinities, densities, and you see these individual periods when the density is very well homogenized. And those periods correspond to times when you actually can see vertical velocities. These are vertical velocities in centimeters per second. So for those of you who are atmospheric cloud people who are used to thinking of vertical velocities of 10 meters per second, I get it, we're wimpy in the ocean, but this is still pretty amazing when you think that a 10 centimeter per second vertical velocity is 8.6 kilometers per day. Right, so it's taking 12 hours to go from the top of the ocean potentially to the bottom of the ocean. Okay. Whereas in other parts of the ocean, as we'll maybe talk about later, it can take thousands of years to go from the top of the ocean to the bottom of the ocean. So convection is doing this extremely quickly. Now, one of the things that convection does when it stirs the water column is it takes the surface layer quantities, such as well-oxygenated waters, and moves them down to depth. And there's a quantity that chemical oceanographers use called apparent oxygen utilization, which looks at how far below saturation is the oxygen in the ocean. And if you look at that quantity, here's a map of it at 1,200 meters around the world, something should show up, right? That quantity is very large in the Pacific, large in the Black Sea, somewhat large in the Northern Indian Ocean, and very low in the Mediterranean and Northwest Atlantic. So these are places where the fact that oxygen is high at the surface, as that high oxygen signal has been brought into the ocean interior. And you'll notice that it's kind of concentrated in the North Atlantic. There is some hint, if I were to expand the scale, you would see some hint of it in the Southern Ocean as well. But it's much more spread out there. Convection also plays an important role in variability. This shows a paper by Annika Reinkers showing that she compared a bunch of climate models and looked at places where there's deep convection occurs in the Pacific, and you can see that there's a sector here in the Weddell Sea where a lot of climate models have variability, and but the characteristics of this variability, if you look at the spectra, you basically just see a point cloud here, right? You don't see any, it's not like everything's peaked at the same amplitude, which it would be for El Nino. There's lots and lots of variability in this. Dan earlier was telling me that, at University of Washington, everything is white noise. This is white noise, right? And on average, this is white noise, or red noise, right? But there are models that show relatively peaked variability, and one of them was described by Hannah in a very important paper in 2015, where you see this polynya open in the Weddell Sea. So it shows an off state of convection and an on state of convection. And there's some evidence that that may in fact be happening in the real world with some similar periodicity. This is the 1975 Weddell polynya. And back in 1964, there was an early satellite that went up, early Nimbus 1 weather satellite that was up for 3 weeks. And so no one for years looked at the data, because why would you look at a satellite that was up for only 3 weeks? But it turns out that there is evidence that there was a similar polynya in that region in 1964. And most recently, in 2017 and 2018, it appeared again. So we'll come back to that later. There it is in 2017. So, some goals for this talk. I want to talk about ocean convection, where, when, and why we care. So where, I want to talk about what factors control the current localization of deep convection to the North Atlantic as opposed to the North Pacific. We went back to that AOU plot with blue in the Atlantic and yellow in the Pacific. Like, why does it look like that? When? How can it vary over decades, and what factors control this timescale? As we will show, there's some easy ways in which you could imagine convection varying over decades, like a capacitor model where it takes time to build up light water in the subsurface ocean. This is not what's happening. And then some aspects of why we care. Liz and Hannah can give you a lot of physical reasons for why we care about this, right? In terms of how convection affects the intertropical convergence zone or the atmosphere. I want to talk a little bit about some impacts on chemistry and biology. Okay, so let's talk about convective geometry and the hydrological cycle and the history of thinking about this. In some ways, the history of thinking about the hydrological cycle and convection really goes back to Luigi Marsigli, who was a diplomat from Bologna to the court of the Ottoman court, the Sublime Porte, in 1683, who's, being a diplomat at the time also meant you were a spy, so he spent some time studying why it was that the Turkish Navy was able to sail ships up the Bosphorus against the current, the surface current. And he realized that there was an overturning circulation, and he realized that that circulation was driven by the fact that the Black Sea was fresh and so the water flowed out, but the Aegean was salty, and so the water flowed in. And this is a reverse overturning circulation from the one that we're thinking about. In 1961, Henry Stallman published a classic model which shows that the freshening of the North Atlantic, the fact that you have an excess of precipitation over evaporation in high latitudes, freshens those waters and tends to put a brake on the overturn. In 1983, Bruce Warren noted that the Pacific is fresher than the Atlantic, and he argued that this was from two processes. One is the fact that the atmosphere transports fresh water from the Atlantic to the Pacific, and the other is that the Pacific, especially the subpolar North Pacific, has lower evaporation than the Atlantic. And this tends to make the Pacific light, the Atlantic dense, and then the circulation that results from this reinforces that. In a paper that I wrote in 1999, which I understand some of you are going to read in Liz's class later in the semester, I was at the time thinking about how we could drive the overturning circulation without requiring lots of turbulent mixing in the ocean. And one thing I realized simply looking at the cross-section of ocean salinity was that the waters that enter the pycnocline from the south, the upper sphere of light water, are fresh. And so that the idea that there's a net freshwater transport into the Southern Ocean plus upwelling in that region converts dense waters that are relatively salty and cold into light waters that are much fresher but also fairly cold. And that water is then, that light water can then be moved northward, injected into the pycnocline, and warmed by diffusion. But the main step of turning the dense water into light water is this freshening in the Southern Ocean. In subsequent papers using idealized geometry models, Palachesi and others, again, these are the kinds of models that Liz uses, show that you can localize the overturning to a narrow or more polar basin. And these models basically assume that the hydrological cycle works that in a narrow basin, you have freshwater flux from the tropics to the polar regions, but you're going to have less of it in a narrow basin than you are in a wide basin. And since you only have one overturning to carry away the freshwater anomaly, the narrow basin is in general going to win, all else being equal. So it again goes back to the Warren mechanism, but without requiring an interbasin freshwater transfer. Okay. So the implication is that the hydrological cycle localizes the overturning to the North Atlantic. That's the implication. Except, and so we would expect this then to mean that under warm climates, the hydrological cycle might be driven away from being, well, we'd expect that under warm climates this hydrological localization to the North Atlantic would operate more strongly. However, there have been a couple of recent papers. This one is by Natalie Burles. There's one that just came out in 2022, where you can think of this purple curve, which I believe is biogenic opal deposition at the ocean bottom of the Pacific, as a measure of overturning in the Pacific. And one thing that this shows is that during the Pleistocene, there was a lot of deposition. And they interpret this as saying that in this warm climate, there was more overturning. And there are other lines of evidence that suggest that in this warm climate, there was more overturning. There's also other evidence, this is from a paper by J.B. Ray et al., that suggests that during the last glacial maximum, there was also more overturning. And Hannah recently published a paper on this in the North Pacific as well. So how does this work with hydrological localization? Well, in the last couple of months, I've been working on a box model to try to understand tipping points between the basins. And so I'm going to lead you through what that model looks like. The basic idea is that you have a single deep ocean box, and I've unfolded the ocean so the Atlantic is on the left, the Pacific is on the right, and the Southern Ocean is here in the middle. And the idea is that you can have overturning in either the Atlantic or Pacific basins that is driven by the available potential energy that arises from the difference in density between the low latitude and high latitude boxes. And that available potential energy goes as the reduced gravity, the gravitational constant times the difference in density over the density times the depth squared of the low latitude layer. Okay. And then there's some fudge factor here that turns that available potential energy, which is in units of meters cubed per second squared, into meters cubed per second. So this is you can think of this as proportional to F, but it covers a whole bunch of physical processes. This is like, there are people who spend their entire careers basically looking at overflows or mixing, or the effects of geometry on circulation. It's all buried in here. And this has been shown to work in quite a large number of model simulations, all of them though at coarse resolution, so keep that in mind, and even in the laboratory by Youngey Park. Now, within the Southern Ocean, this overturning is supplied by an upwelling of water in the Southern Ocean and freshening there. But that, if you actually look at the volume of that upwelling, it's much larger than the overturning in the north. And it turns out that eddies, which I'll talk about in a minute, can act to fight that. And so I'm just going to put that formula up, and we'll come back to it in a minute. We also have upwelling in the Pacific and the Atlantic, which is what the scaling you get from an effective diffusive balance. This goes back to Frank Bryan's work, 1987. And it goes as a diffusive coefficient times the area of the basin over the depth of the line. And finally, we have an exchange term between these two basins that goes as basically the difference in available potential energy between them. And then freshwater fluxes. Okay, now I want to return to that point about eddies. The ocean is full of turbulent eddies. We start off with this distribution of temperatures and allow them to be advected by the surface currents. This is what you get. And you can see that there's lots of this swirling weather in the ocean. What does it do? Well, it does two things. The first is that if I have some tracer gradient of C versus X, the eddies will drive a diffusive flux of tracer down that gradient according to using the Fickian diffusion law, where the Fickian diffusion coefficient has units of length squared over time. That's fairly straightforward. There's also, in addition to the transport of tracers, the eddies, however, also flatten interfaces. And this process is quite similar for those of you who think about jet dynamics and the vertical component of the Elias and Palm flux. This is basically the same thing. The idea that if I have a thick layer over here and a thin layer over here, the eddies will actually act to homogenize the layer interfaces. And that corresponds to an advective effect. And that acts to fight the Ekman flux in the Southern Ocean. Okay. And this idea was first proposed by Peter Gent and Jim McWilliams in 1990. So both of these require a diffusion coefficient. And if you look at the modern version of climate models and ask, what did they use for a diffusion coefficient? You come away somewhat depressed. And the reason you come away somewhat depressed is that some models use constant coefficients. Gen uses 500. The Italian model uses 2,000. The factor of 4 difference in the coefficients there. Some scale with grid spacing. MPI actually ends up smaller than that on average. Others scale up to the baroclinic growth rate, so it's proportional to the isopyctal slope. So there's 3 models that do that. I'm just putting this quote in by Bob Stewart, which points out that those of us who are theorists like to think that we're lords of the universe, but in fact, observations are really, really important in constraining what we know about the world. And just to give you a proper skepticism of climate models, Here's the theory-based estimate of the mixing coefficient, and here's Ryan Abernathy's observation-based estimate of the mixing coefficient. And you'll notice that they don't look anything like each other. For now, since I'm using a box model, I'm just going to use a baseline value of about 1,000 meters squared per second, which is what you get by looking in these boundary currents. And the reason I'm going to do that is that it turns out that these two values actually match up pretty well in the boundary currents. It's only when you get away from the boundary currents that you get very different answers. But it should be noted that this is an area where models differ, and we'll see one of the implications of that. We'll come back to this for each of the problems I work on in this talk. Okay, so having chosen my diffusion coefficients, having chosen a vertical diffusion coefficient, well, let's go about calibrating these fudge factors and freshwater fluxes. So the pictocline depth in the Atlantic is about 420 meters, and all of these numbers depend on exactly where you put the boundaries of your boxes, so don't worry too much about a difference of, is it 420 or 425 or 430? This just gives you qualitative results. Notice that the pictocline of the Pacific is actually shallower. The temperature and salinity in the Atlantic, 16.2 and 35.8. So the Atlantic is cooler but also saltier than the Pacific. This means the Pacific ends up standing high relative to the Atlantic. The high latitude temperature salinity, on the other hand, is the temperatures lower and salinity is higher in the Atlantic relative to the Pacific. If we look at the differences in density, the density differences between high and low latitudes in the Atlantic and Pacific aren't all that big. And so the driving available potential energy is not all that different. And yet, when we look at the estimated overturning and mixing fluxes, this ends up at like 20, this ends up at like 10, with this 18 and 6 being the components that are driven by overturning. So these are very different, and yet these are pretty similar. And that's not all explained by the difference in pictocline depth. If we use this to back out a freshwater flux that would explain the differences, we get a flux of 0.45 spheroids in the Atlantic and 0.34 in the Pacific, which is opposite of what I just told you the idealized models use. The idealized models all have more freshwater flux in the large basin and less freshwater flux in the small basin. But in the real world, it goes the other way. I first noticed this when I started trying to calibrate my box model against my coupled climate model and realized that I had about half as much freshwater flux in the Pacific and the Atlantic. I was like, wait a minute, is that real? And then I looked, and there's lots of evidence that that is in fact the case. Nobody talks about it because it actually makes the problem of how to localize your freshwater, your overturning the Pacific harder. So best to sweep it under the rug. However, I can sweep it under the rug with a fudge factor. So that's what I do. I have this resistance factor, and what I find is that my resistance factor is twice as large in the Pacific as it is in the Atlantic. So these are two definite surprises. First is the Pacific gets less freshwater flux than the Atlantic because a lot of the water goes into the Arctic. And the second is that the Pacific is much less efficient at converting available potential energy to overturning. So what's going on here? What's going on here, I think, is that if we take a schematic cross-section of the Atlantic, and this would be the low latitudes, the high latitudes, the Atlantic is denser than the Southern Ocean. So the North Atlantic deep water is denser than Antarctic intermediate water, which means that as it sinks, it gets a kick both from the shallow AP, but also from the intermediate water. So resistance is low. Not futile, but low. The Pacific, on the other hand, is lighter than the Southern Ocean. And so you have a system that looks like this, where the sinking is opposed by the AIW, and so you have higher resistance. And so in the model, what we do is basically let the resistance be low when the northern basin is denser than the southern basin, and let it be high, double when the northern basin is lighter than the southern basin, and we've got a hyperbolic tangent transition between the two. Yeah.
Now, you say that that's true. How come that's true?
How come?
I mean, if there's a short answer, because I'm ignorant of this stuff, but I'm interested.
How come this is true?
Yeah, why is the Pacific lighter than the Southern Ocean and the Atlantic is denser than the Southern Ocean?
That basically that is the question. Right, that's
okay.
it.
I thought that was asserted and
It
everybody knew that.
it is the
Okay.
case, but we don't know why that's
Okay.
true.
Okay.
Right, and so to some extent, the fact that as you make the Atlantic lighter or the Pacific lighter than the Southern Ocean, that it gets harder to derive overturning,
Yeah.
actually acts as a positive feedback.
Oh, okay, that
Right.
sounds interesting.
Because then you make it lighter than the Southern Ocean, and now you can't export the fresh water anymore.
Hmm.
You can't export the fresh water to the deep, so it can build up more.
Okay.
That's the quick answer.
Okay, thanks.
We also run a counterfactual simulation where we do what everyone would have expected and increase the Southern Ocean. We increase the Pacific flux to 0.6 sphere drips. Here's our Atlantic flux, Southern Ocean flux. And what we basically find is that the Atlantic deep water comes out of this as a temperature of 3.94, salinity of 35.11, and overturning of 19 sphere drips. Pacific is 4.15, 34.8, 15.1 sphere drips. These are not bad numbers. If I go to an oceanographer and say, here's our numbers for the North Atlantic, if I had a coupled climate model that produced these, I would be happy. The only difference is here, and I can tell you, having analyzed coupled climate models, so this will probably confirm, coupled climate modelers don't spend a lot of time thinking about the overturning of the North Pacific. Because it's low, right? It's low, doesn't matter, right? No, maybe not. So we're going to actually start with counterfactual flux. And what we're going to do is set the interbasin freshwater flux. We'll let it vary between 0.3 and minus 0.3 sphere drips. We get a pretty good fit to observations of about 0.15. And then we scale the whole, and we do that for our base case here at 1. And then we scale the amplitude of the hydrological cycle up and down from near 0 to 2, twice 2 days. So this would be the equivalent of 10 degrees of warming. And this would be like putting the hydrological cycle back 10 degrees of cooling or 20 degrees of cooling. It would be much colder. And what you're looking at here is the Atlantic overturning. So you can see there's this huge range where the Atlantic overturning is pretty much in the 20 sphere drip range, 18 sphere drip range. Right? This is, in the counterfactual case, the Atlantic overturning wants to be in this range, and as you increase the freshwater flux, it collapses. The Pacific overturning, you can get a value of that's like today is with a little bit less freshwater transport, and as you increase the Pacific overturning, it also collapses. When you increase the hydrological cycle, it also collapses. So this produces the classic case where as you increase the hydrological cycle, the high latitudes get light. They get lighter than the Southern Ocean or lighter than the tropics even, and they just collapse. The overturning collapses. In fact, it goes negative here, which is what you get when you have a high latitude that is lighter than the salty, warm tropics. Right? Okay. Interbasin transport kind of modulates this a little bit. So as I drive fresh water from the Atlantic to the Pacific, or from the Pacific to the Atlantic, the overturning declines a little bit. And where I collapse the overturning in the Atlantic, that changes a little bit. Here's what happens if we start with the fluxes, though, which go the other way, where the Atlantic has more freshwater flux than the Pacific. Here's the Atlantic overturning, and X marks where we think we are today. And here's what the Pacific looks like. You can tell these do not look anything like each other, right? These do not look anything like the previous picture. So what's happening? We can collapse the overturning in the Atlantic by reversing the interbasin freshwater flux. And if we do that, we also turn on an overturning in the Pacific. We can increase the overturning in the Pacific by reducing the Atlantic freshwater flux, or reducing the amplitude of the hydrological cycle. because as we do so, we reduce the contrast in salinity between the Atlantic and the Pacific. We also can produce an overturning in the Pacific by increasing the freshwater flux. And we do that because the hydrological cycle in the Atlantic is stronger than the hydrological cycle in the Pacific. So if we increase the freshwater flux, we lighten the polar Atlantic relative to the polar Pacific. Right? So this is decreasing the gradient between the Atlantic and the Pacific. This is increasing the gradient between the Atlantic and the Pacific.
Can you remind me, when you're saying scaling the hydrological cycle?
I'm just multiplying all fluxes by the same amount.
Got it. So this isn't like a.
So I'm not changing so you can think of it as the horizontal axis is changing the geometry of the hydrological cycle, like how much of it is going across continents. And the vertical axis is changing the amplitude. So in this case, changing both the pattern and the amplitude of the hydrological cycle can produce changes in North Pacific overturning. And I don't think anybody has shown this. I'm not actually going to go into the details here, keep the time. But it turns out that when you actually put noise into the system, you get even richer behavior. So this is a case where I double the initial freshwater flux, and you're looking at the transports here. Both the North Atlantic transport overturning collapses and actually becomes a reverse circulation. The Pacific collapses even faster. But then the density in the Pacific gets lighter and lighter, or heavier and heavier, and at some point it crosses the threshold where it's heavier than the tropical Pacific, and it turns on. And then it turns on for a while, you get large amplitude fluctuations, and then it starts to turn off, and the fluctuations actually decrease as you move towards a boundary. This is really remarkably rich behavior, and we're still analyzing it. We have found that there may be some interesting bifurcations here. There are regimes where this will produce oscillatory behavior. That's future work. So this very simple model can produce this very rich set of behaviors, some of which help explain phenomena like how we get overturning in the Pacific in both warm and cold climates that previous models were not able to do. A caveat here, does this depend on how we represent mixing? Remember, I talked about eddy mixing and how the models give very different answers. The answer is yeah, it actually does depend on mixing a lot. So we have three cases here. Here's our baseline case for the Atlantic and the Pacific overturning. The top case is low levels of mixing, and at low levels of mixing you can see that the Atlantic overturning becomes more stable, and the Pacific overturning shows a single tipping point. If we increase the mixing to 2,400 meters squared per second, then this region disappears, the overturning threshold goes up to higher interbasin freshwater fluxes. We tend to smooth this out. Presumably there is still some of the same structure if you continue going to higher and higher values. But so at high levels of mixing, we've got more sensitivity to the interbasin freshwater flux than we do at low levels, right? So mixing, again, these subgrid cell parameterizations matter. You don't necessarily need to know all of these details, right? If you're my students, I would say you don't need to know the details, but as climate scientists, what you need to take away from this is that these subgrid scale parameterizations that some people spend their lives trying to measure actually really matter, right? And you cannot simply take a climate model and run it and think you've got the truth, because the climate model makes one assumption about this, which may not be the right one. Okay, so results from part one of this talk. The hydrological cycle puts less fresh water into the Pacific than into the North Atlantic and Arctic, and this means that you can either increase or decrease the hydrological cycle to open up convection in the Pacific. And there's some indication that this has happened in the past. This simplified model gives very rich tipping point dynamics, and it can give you variability with noise. All right, so that's part one. That's the where. Now I want to move it into when. So analyzing Southern Ocean variability. And this work was published during the pandemic, so relatively few people have seen it. And although I think one of the grad students said they'd actually read this paper, so I'm very pleased. So this was work that was done with a coarse resolution version of the GFDL ESM2M model, which has a relatively realistic representation of a wide range of physical processes. It has model ACC transport mean density gradient across the ACC better than most, like all but 4 of the 30-odd CMIP5 models. That's actually true for all of the versions of the model, with all of the versions of lateral mixing we have. We often sit right up near the top there. We have relatively low parameterized lateral diffusion in the Southern Ocean for this particular case. So some caveats: this model doesn't resolve eddies, it doesn't capture deep overflow dynamics, and so that may limit the realism of the model. What you're looking at here is the RMS interannual or decadal temperature variability of the sea surface temperature in degrees C. What you'll see is there's El Nino, there's the North Atlantic current. So where is this? This is what Tater's working on, right? And you can see there's lots of variability there. There's that strong gradient in that current shifts north and south. Here's the Southern Ocean. So the strongest, the largest areas of variability is this convective region of the Southern Ocean, where, as we saw earlier from Garankis, many models have this variability. And this shows the annually smooth temperature anomaly. So we have these convective time periods where we get cold at the surface and warm, cold at depth and warm at the surface, and then there's non-convective time periods where it's cold at the surface and warm at depth. The salinity anomaly goes the other way. So the time periods when it's warm at the surface are also time periods where it's salty at the surface. And one of the things that you'll notice here is if we look at the density anomalies are surface trapped. We get a larger density anomalies at the surface than we do at depth. Now this is puzzling, right? Because if the density anomalies were building up at depth, it's really easy to see how you could have 50 or 100-year time scale develop there, right? But how do we get these multi-decadal oscillations at the surface with a period of about 50 years?
Is this region coincident with that Antarctic current?
The Antarctic circumpolar current runs north of this region.
So the jet that it provides to the circulation is not a factor, or maybe it is a factor?
It is somewhat of a factor,
okay.
but there's the Weddell Gyre. This is part of the Weddell Gyre.
Okay.
Right, so it's basically, the ACC runs basically right along the northern edge of this. Okay, so what we did was we looked at, we took rotated empirical orthogonal functions and looked at both the salinity and temperature together, and what we found was that the first mode of variability in salinity and temperature corresponded to that convective region, where you get warm and salty anomalies, or cold and fresh anomalies in the Weddell Sea. We then looked at other modes, and the particular mode that was interesting to us was the third mode of variability, in which we found a fresh anomaly along the prime meridian and warmer anomalies to the north of this convective region. Then when we plotted those against each other, the amplitudes of those anomalies, we could see that they were going in phase with each other. Plot them in time and plot them against each other, we see we have this oscillatory behavior. And we were then able to just model this as a coupled oscillator, where the first mode of variability, the convective mode, tends to be unstable. And this is because as you bring warm water to the surface from below, you get more convection, you cool off more rapidly, and that tends to destratify the water column. But then that tends to produce a positive anomaly, a freshening in the eastern Weddell Sea. And that freshening in the eastern Weddell Sea, as it builds up, tends to damp this. And so if we take these equations and plot them against the mobile rates of change, we get a fairly good fit. And so the basic story is that convection of the Weddell Sea corresponds to warm, salty water at the surface, which increases a pattern where you have warmer water to the north and fresher water to the east. That fresher water to the east circulates into the Weddell Sea and shuts off the convection. And you have cold water in the Weddell Sea at the surface. That produces a warm anomaly to the east, a salty anomaly to the east, which convects into the Weddell Sea, becomes dense, and turns the convection back on. And so this is really a delayed oscillator type of model. And so the thing that connects those anomalies is the wind stress. So it turns out that if you look at the Weddell Sea SSTs and the wind stresses, when the Weddell Sea is convecting, you have higher wind stresses polewards and weaker wind stresses equatorwards. You get this basic shift of the winds away from the warm water. And then that reduces the upward mixing of salinity along in this sector. So the picture that then emerges from this paper is that if you start off with deep convection in the Weddell Sea, you increase the salinity in the western and eastern Weddell, which gives you more cooling evaporation, which actually acts as positive feedback loop. You also, however, you also increase the westerly winds to the east of the convection. Sorry, you decrease, this is a feedback diagram, right? I tell my students, arrows show positive relationships, dots show negative relationships. So negative relationship there, right, between the SST and westerly winds, which then change the vertical mixing and also the effective salinity supply in the eastern Weddell, so that about over 10 years, the salinity in the eastern Weddell becomes higher than the salinity in the western Weddell, which then, as it propagates in here, acts to, if we go around this curve, we've got a negative relationship, positive, 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 positive. So this is a negative feedback with a delay. And the result is to generate an oscillator. In water mass space, this looks like the following. So we take salinity here and temperature here. In our off state, we end up somewhere down here. And then in our off state, what happens is that over time, we get saltier as salty water gets mixed in from the eastern Weddell. Then at some point, the eastern Weddell is blue, the western Weddell is red. And so we start off here, and then what happens is we get saltier, and at some point the eastern Weddell and western Weddell have a sort of similar density. Parts of the western Weddell become dense enough to initiate convection. This convects, both regions go up. Then the winds relax, and so the eastern Weddell starts to get fresher. The western Weddell comes down here, and we end up in this state, and then the cycle resets again. So we both proceed in counterclockwise directions around these loops. Okay, so this is for one model. So I've shown you can't ever necessarily trust one model. So let's see what happens when we change the mixing. We see the previous work we've shown that as we change the eddy representation, we get very different answers. In our control case here, which shows mixed layers over 500 years, we get periodic convection, buildup of heat, convection, buildup of heat, convection, buildup of heat, convection. The case I just showed you was our low eddy diffusion case, where it's nice and regular. If I make the eddy diffusion high, I don't see it at all. If I make the Jekyll-Williams diffusion more effective, I can just shut this off altogether. Right? So the representation of eddies matters, and if we plot where we end up in the water mass spectrum, what we see is that in our low diffusion or high diffusion case, we always end up in the on state or near the on state. In our low diffusion case, we always end up in the off state. However, it does turn out that the locations of where the variability occurs then shift, and we have not yet analyzed that. In terms of whether this mechanism is realistic or not, we can look at individual parts of it. We can't really judge this over the entire cycle because we don't have good measurements for 40 years, but we can look at different parts of the relationship. So here's the relationship between SST and westerly winds in our model, and that's bad. Sure. So these are the two models that we had in the dashed line, which you can't see here, is the ERA interim. So ERA interim shows the same behavior, right? The models have about the right slope. Even a 3-degree atmospheric climate model has about the right relationship in terms of its sensitivity to changes in temperature and changes in, this is the geopotential height difference versus the momentum flux. So, similarly, if we think about effective salinity being the driver of convection, Ethan Campbell's 2019 paper shows that it is in fact large changes in salinity of the surface that drove the Weddell plane and not subsurface changes. Okay. So again, lessons from that section is that we have this mechanism that couples winds, the hydrological cycle, and convection. That they are related. The hydrological cycle is an important driver of convective variability, but it's modulated by the winds. We'll move to part 3, which is why we might care. So I'm going to talk a little bit about the impacts of convective sensitivity on ocean biogeochemical cycling under climate change. My group for the past decade has been running versions of the GFDL climate model with different amounts of lateral mixing. And then once you have that this suite of experiments, you can examine a whole range of phenomena from El Nino to Southern Ocean climate variability to climate change. And so one of the things that we've done is increase carbon dioxide by 2x, double it instantaneously, and quadruple it instantaneously, and then look at the response and the linearities of the response. It shows the change in surface temperature for 6 different model runs. And to first order, what you're going to see is that the different colors lie on top of each other. So the global mean surface air temperature isn't terribly sensitive to this. And the sensitivity, so here's delta surface air temperature in the doubling and quadrupling case, lies pretty close to the 2-to-1 line. So air temperature responds relatively linearly and is not all that sensitive to the mixing coefficient. However, when we start looking inside the ocean, we look at the change in the volume of hypoxic waters, we can see that the 4x CO2 case actually, we can find cases where it goes in opposite directions than the 2x CO2 case. And this is relevant because the way in which many climate model changes or climate change impacts are assessed is by running 4x CO2 cases, looking at the pattern of changes that emerge, and then using that to project onto the historical. This tells you that that's not going to work for oxygen. It also tells you that the results are going to be very sensitive to whether you have the right mixing or not. And this is another example of changes with waters that are undersaturated with respect to calcite. So these were waters in which calcium cell organisms will have their shells dissolve. That's also quite sensitive to the mixing. You can get factor of 4 difference, or factor of 3 difference in that, depending on which mixing you use. And we think that part of that is, again, convection. So I'm showing here profiles of radiocarbon in the North Pacific. Radiocarbon is generated by cosmic rays interacting with nitrogen in the upper atmosphere. It then enters the ocean and decays with a half-life of about 5,800 years, and folding time of about 8,000 years. And so if you can think of each of these ticks as about 320 years of age. And if we look at the observed radiocarbon in the North Pacific, that's given by the symbols here, and the different models in my suite are shown here. And some of them basically have relatively low rates of radiocarbon in the pre-industrial control, which is suggestive of deep convection in the North Pacific. As we increase the CO2, what we see is that these different simulations peel off. So that the low mixing case has relatively little convection, and it moves a little bit to the left, gets a little bit older. This case with about twice that level of mixing moves over further. 1200 case and moves over a little bit. But then when we quadruple, everybody goes far to the left. So the biggest response to doubling CO2 is really seen in these intermediate mixing cases, whereas the biggest response to quadrupling CO2 is seen in the high mixing cases. So some conclusions. The current geometry of the hydrological cycle may allow for either Pacific versus Atlantic tipping points under both warm and cold climates. And that is a new result. The interaction between convection winds and the hydrological cycle in the Southern Ocean can produce regular oscillations in a climate model. And the shutoff of convection can produce nonlinear effects, particularly on interior chemistry and age under global warming. All of these results are sensitive to how we represent subgrid scale turbulence. We finish off with thanks to my collaborators, Maria Pradal, Darren Wajay Brett, staff or faculty at Hopkins, former students Jordan Thomas and Alexis Ball, undergraduate Sarah Reagan, who's now at the University of Washington, Cassie Speller, Grace Ringline, and Johnson CC, who are undergraduates with me, either interns or senior thesis students who participate in the convective work. So with that, I'll thank you very much, and I'll happily take questions.
Any students have questions?
Ruben.
Yeah, that's a very interesting talk, and from a non-oceanographer's perspective, I quite didn't understand what tipping point you're talking about, and also if you go back to your diagram for the first part where you talked that Pacific has a smoother, you were identifying tipping points, and Pacific I did not
Right.
get what's that.
So let's go back to let's actually just go back to a single time series first.
Okay.
Okay, actually we'll go back to this one without the noise. So what we see here is that over time, over 2,000 years, what happens if we increase the freshwater flux from our present, we start off with our present day conditions, we instantaneously increase the freshwater flux by 70%. The amplitude of the hydrological cycle by 70%. And what we find is that initially that gives us a first tipping point. Right? The overturning collapses and it stays collapsed. So the North Atlantic stays in a collapsed state. So that would be an example of what we mean by tipping point. Right? The Pacific collapses and then it comes back. Now, you're asking how we define a tipping point, and that's actually a subject of debate in the tipping points community. Is it that you switch rapidly from one state to another, or that you switch in such a way that you have irreversible change, or that there's some hysteresis in the system? I have not yet explored hysteresis in this, but I have good reason to believe that this state will exhibit hysteresis. Right? That if I start from this state and then decrease the overturning or decrease the freshwater flux systematically, that it will stay in that Pacific state for some period of time.
Okay.
Question from online, Evan Meeker says, in your interbasin overturning model, you have a resistance factor that doubles when the given basin has lighter water than the Southern Ocean. You then show that the model with white noise has strong tipping point behavior. Would those tipping points still be so strong if you had a more realistic resistance factor that smoothly gets stronger as the density difference gets stronger?
So I do actually have a resistance factor that gets stronger, smoothly gets stronger as the density difference gets stronger. There's a hyperbolic tangent transition there. But it is a reasonable question, and I've sort of calibrated it from the data, right? I know that I have a factor of 2. But Yeah, you could imagine that it could be much smoother than that, or that it could continue to increase, I could drop. There's many ways of going between one or the other. I expect that would produce differences in exactly where the tipping point occurred, but I don't expect that it would fundamentally change the behavior. Other questions?
Oh, go ahead.
Oh,
Mr. Johnson?
really interesting talking. Thank you for coming to visit us. The discussion about salinity advection and the mention of mesoscale eddies makes me wonder, is there a larger scale of eddies or organization, like a synoptic scale eddy, that does some of this advection of salinity that seems so important? And if so, how are those synoptic eddies organized? Are they constituents, or are they created from constituent mesoscale eddies?
So, probably not in, okay, so there is a synoptic scale in the sense that there are larger scale gyre circulations. So it's particularly in the Southern Ocean, there's what's known as the Superchar Circulation, right, which links the Indian Ocean and Atlantic. To a large extent, those circulations can be simply predicted from the wind stress curl. And what the eddies do is they break that circulation down into jets, but they don't fundamentally change it. So it's similar to how one might think about the atmosphere of Jupiter or Saturn, where you have a large-scale jet circulation that then gets broken down into steps, right? Rather than the Great Red Spot, where the circulation is fundamental, the eddies are fundamentally pumping energy into that large scale.
So does anything organize salinity gradients in an analog to fronts in the atmosphere? Because it would seem that's a really efficient way to accomplish this advection. And if you're relying on eddies on the mesoscale, maybe that's a little stochastic.
Yeah, so the really interesting question that goes along with that is, when you organize eddies into a front, we do have frontogenesis in the ocean, right? Do those fronts serve as barriers to mixing, or do they serve as blenders? And many of the models assume that they are blenders. However, they are fronts. They maintain tracer gradients. There's good reason to believe that they're actually barriers. And so I have a review paper with Ryan Abernathy that came out last year in volume about ocean mixing. And one of the things that we argued is that the theorists for years have said, we can explain the mixing coefficients in terms of a velocity which we get from baroclinic instability or ED theory, right, times the length scale. And then the mixing length scale is just the eddy length scale. Well, that's clearly wrong, because it does seem like the length scales are suppressed in frontal regions. And if you think about why that would be, imagine you have an eddy going by and it's being carried by a current. Right? If you're away from that eddy, you only feel part of that, the eddy goes by, you feel a little wave. You don't have time to get wrapped around the eddy, right? And so the eddies are, the fronts, the jets, are actually serving as barriers to mixing rather than blenders. And that effect is not in any of the current generation of CMIP models. Right? There's a couple of efforts that have been made to try to implement it, but it's not in a production run as far as I'm aware. So,
Thank you.
Another question? Yeah.
So, thinking Polania, see if I can go back and dig from the dregs of, however many years ago it's been. Really getting old. I guess the question is, so as you freshen the Southern Ocean-ish in climate change,
Yes.
do you actually expect that delay to increase, or do you think
That's a great question.
full-blown shut off, sort of?
I
You
would
see papers like that.
That's right. So, as you're well aware that Casimir de la Vergne has
Yeah.
that extremely highly cited paper where he shows that the models that have convection tend to cool faster in the Southern Ocean than models that don't.
Right.
And we see sort of similar behavior here. That if you have convection, you get a different response of temperature, a slightly different response of temperature change in the Southern Ocean than if you don't.
Yeah.
Right. So I expect that is true. that it does shut it off, but then the question is, for how long?
Right, like, is
Right.
it just an increased delay, or is it like a?
Yeah, and that has to do in some sense with the flushing time of the system, right?
Right.
Right,
And
yeah.
how well you convince salinity to overcome the
That's right.
freshwater. added
That's right.
freshwater. But that also depends on where the freshwater goes, right? We don't model that well either. We are terrible at modeling Antarctic sea ice and
Right.
where it ends, where the water's
Right.
supposed to end up.
Yes.
So
Yes.
I'm just kind of
Yeah.
curious.
What's somewhat surprising about this model is that even though it has a very large temperature bias in the summertime Antarctic, it basically gets the sea ice dead on. It gets the wintertime right, so fine, right? You put the heat, too much heat in the summer, and then you just get rid of it, right?
Right.
So it's a summertime cumulus bias, but yeah.
In this oscillatory process here, there's an atmospheric response. I guess, what is that atmospheric response?
It's basically what you might expect from thermal wind, right? That you warm the Southern Ocean, and so if you imagine 500 millibar height, that's going to go up, so you have a lower 500 millibar height gradient. And the eddy momentum flux in the atmosphere, in both observations and the model, is proportional to that height gradient. And that eddy momentum flux is what is supplying the wind stress at the surface, right? So as you increase the height gradient, the surface winds drop. But the key link to that is the 500 millibar transport, or the upper atmospheric transport, the eddy momentum transport, actually at 200 millibars, the strongest. So, yeah. Liz?
So I really like that contrast between the LGM and the Pliocene. We could get specific overturning in both of them, so I thought about that too. But there's also, I mean, those two periods were not exactly the same, right? I mean, the LGM, you've got these ginormous ice sheets that are probably doing things to the atmospheric circulation. And
Right.
the Pliocene was, I forget if the isthmus was, Panama was open then or not,
Yeah,
or.
yeah.
So I'm curious how you would work those kind of details into the model. Would this just all be how you parameterize the freshwater? And part of
Yeah,
why I'm-
so one of the ways in which you could, for example, work the Isthmus of Panama is by reducing interbasin exchange resistance, right? So that I would expect that would change things. I was actually thinking about this last night. Not clear how you work the winds in, right? So one of the things that I haven't talked about here is I have wind-driven upwelling in the Southern Ocean. I don't have wind-driven upwelling in the Northern Ocean and the associated density transports that go along with that as a way of keeping the model simple, right? But it is very likely that this same process of convection to winds to salinity to convection is also operative in the North Atlantic as well. And we just haven't worked it out as well. Right? I mean, John Marshall has talked about it in terms of temperature, but I think it's actually salinity. And I think there's some evidence for that with the great salinity anomalies. So,
That probably also matters on what model you're using.
yep, it does. So I was telling Tedra I had a 2014 paper where we used the GFDL ESM2M and ESM2G models. So they have identical atmospheres, identical sea ice, identical land models, identical values for the parameterization, and identical grids in the atmosphere, and different ocean models. And one of them has a 70-year variability in the AMO, and the other one has half the variability, amplitude variability in a completely different frequency. So, yeah, and some of that has to do with how the mean state then changes where the Aleutian low, or not Aleutian, I keep saying Aleutian, the Icelandic low is, and how the Icelandic low wobbles in response to convection. So convection is a slightly different place. The freshwater fluxes are different. So, because the plumbing of the model is a little different. One's a C grid model, one's a B grid model. So you have all of these very subtle differences that can actually make first order differences in the overturning. And in that case, I was looking at the response of biology, and one of them has a beautiful great salinity anomalies that produce exactly the changes that you would expect, and the other one doesn't. So, yeah.
Any further questions? All right, if not, then I think we should thank Anand one more time.